1.4, rewriting equations and formulas. In the previous section, we were solving linear equations that were written in terms of one variable. In section 1.4, we're going to be looking at equations that are written in terms of more than one variable, and we'll be asked to solve those equations for one of the variables given. So for example, here I have an equation 11x minus 9y equals negative 4. The equation is in terms of two variables, x and y, and I'm asked to solve the equation for the variable y. In other words, isolate the variable y on one side of the equation. So to isolate the variable y, I'm going to subtract 11x from both sides. That brings me to the second line here. And then to solve for y, I'm going to divide both sides by negative 9, which brings me to this third line, which is this original equation solved for the variable y. Y is equal to 11/9 x plus 4/9. So on page 29, if you try number 5, pause this presentation, take a moment and try number 5. So in this case, I'm asked to solve the original equation 5x minus 3y equals 9. Solve that equation for the variable y. So I want to isolate the variable y on one side of the equation. I subtract 5x from both sides of the equation, and then I divide both sides by negative 3. The y is now isolated on the left-hand side, and on the right-hand side, I have an expression in terms of x. Negative 3 plus 5/3 x, which could also be written as 5/3 x minus 3. 5/3 x minus 3. So in this example, given the equation xy minus x equals 4, find the value of y when x is negative 4 and when x is 2. So there are two ways to find the value of y when I'm given specific values for x to substitute. One is to take the original equation, substitute the values for x directly into that original equation, and solve for y. One is to take the original equation and solve for y, and then substitute the values for x. So for example, on this left-hand side of the slide, method 1, I've taken the original equation xy minus x equals 4, xy minus x equals 4, and I've simply substituted the x value of negative 4 in for the variable x in the equation. So in place of x, I have negative 4. In place of x, I have negative 4. Solve for y. Or for the other value of x, for the x value of 2, I've taken the original equation as is, substitute 2 for x, substitute 2 for x, and solve for y. Or the other method is to take the original equation, xy minus x equals 4, take that equation and solve it for y. Isolate the y on the left-hand side. Now once I have the equation solved for y, now I can substitute my x values. First of all, substituting negative 4 for x produces 0, just like it did in method 1. We're taking this new equation and substituting 2 for x produces the y value of 3, just like it did in method 1. So on page 29, you can try number 14. Pause this presentation and try number 14. So here in part A, I have the original equation, xy plus 3x equals 25. I'm directly substituting 5 for x, 5 for x, solving for y, y is 2. Or in part B, taking that same original equation, solve for y, and now substituting 5 for x, 5 for x, and getting that same value of y, again, positive 2. So word problem or application problem, you are selling two types of hats, baseball hats and cowboy hats. Write an equation with more than one variable that represents the total revenue. So total revenue is the amount of money I'm going to take in by selling these hats. And in general, the total revenue is simply the number of items sold times the price per item. If I sell 10 items and each item costs $5, then the revenue is 10 times 5 or $50. In this case, because I have two different products and two different prices, I'm going to have two separate revenue streams, which I've designated here as R1 and R2. R1 is going to be the number of baseball hats times the price per baseball hat. R2 is going to be the number of cowboy hats times the price per cowboy hat. And this would be an expression for the revenue in terms of more than one variable. And here are my variables defined here in the right-hand column. So on page 30, you can try number 37. Pause this presentation and try number 37. So you can see here I've represented the price of visors as P1, price of caps as P2, capital V is the number of visors, capital C is the number of caps, and therefore expression for the revenue, price per visor times the number of visors plus price per cap times the number of caps. So throughout math classes in the past, pre-algebra, algebra 1, geometry, you've learned some various formulas. For example, the formula which relates distance, rate, and time, or the area of a triangle, or the perimeter of a rectangle, and so forth. So in this section, what you'll also be asked to do is to take some of these common formulas, but solve them for a different variable. In other words, typically when we look at the area formula for a triangle, we see that formula in a form where it's solved for the variable A, for the area variable. What this example is asking you to do is take that area formula, but solve it for the height, so that height is the isolated variable. So in this example, area is 1/2 base times height. To solve for h, to isolate the h, I'm going to multiply both sides by 2. That brings me to this second line. Base times height is equal to 2 times the area. And now to solve for the height, all I have to do is divide both sides by the base. Height is 2 times the area divided by the base. So you can take a moment, pause this presentation, and try number 24 on page 29. So the circumference of a circle, that formula is circumference is equal to 2 pi times the radius. To solve that formula for the radius, I simply divide both sides of the equation by 2 and divide both sides of the equation by pi, and I get that the radius is equal to circumference divided by 2 pi. So in this example, you have 21 feet of plastic border to enclose a flower bed that is in the shape of an equilateral triangle. Equilateral triangle, all three sides are the same length, so the sides will be 21 divided by 3, or 7. Problem, express the area of the flower bed in terms of its height alone, so strictly in terms of h. Well, in general, the area of a triangle is 1/2 base times height. For this specific triangle, though, I have a numerical value for the base. The base is 7. So I can substitute 7 for the base, simplify by multiplying 1/2 times 7, and I get an area formula for this triangle, which is strictly in terms of height, 7/2 times the height. The other question to ask on this problem is then, what is the specific area? What is the numerical value for the area of this triangle? Well, in order to determine that, I have to determine what the height is. So you can pause this program and try to determine that area. Try to determine the height, and then multiply by 7/2 to get the area of the triangle. So if you recognize that you have you have actually two 30, 60, 90 triangles, when you draw that height, that altitude into this triangle, you'd realize that the height of the triangle, therefore, is 7√3/2 because of the relationships between the sides in 30, 60, 90, and there's the area.